and I look at the impact of R. I have the following. So if R becomes very, very big, H tends to 0. This is something we expect. And in that case, we almost all the time we have non-equilibrium. And this might be very important for the application I worked on for this particular problem was the heat transfer and composite material. And if you have delaminated composite, for instance, because some stress, mechanical stress on the system or some process manufacturing defect, then you will have R will increase, and the thermal behavior of your composite material will become very, very bad. On the contrary, I have this particular situation. So if R becomes to 0, then I essentially get the normal two-equation solution. The heat resistance that triggers the need for a two-equation model does not come from the heat barrier. The impact on K is not very important. So it works relatively well. This is a numerical simulation. So those are the average temperature obtained from the DNS. So I took a single unit cell volume, so it's not completely smooth, but it gives the trend for the average value, and you see that without any tweaking of parameters, the closure problems gives a relatively good prediction of the field. And if you compare that with measurements, for instance, you have the following features. So it's quite complicated. I'm just going to comment on a few things. So these are the power scale parameters. And these are the, we just look at the, it's very difficult, you don't find a lot of two-equation parameters measurements in the literature. So we were able only to compare in the case of local equilibrium. There are not many people that look at that, except for some particular application, in particular one coming from the aerospace application I will comment later. But for most of the material science in classical composite material, people essentially look at local equilibrium situation. So you see that here, and this is the theoretical prediction here. So it works relatively well. You are never happy with the differences you see, but they are not very, very large. And it's very difficult to, for instance, here people that put 4 significant digits in the measurement of thermal conductivity, I have downside. When I was young as a researcher, and we spent a lot of time trying to measure correctly thermal conductivity, and I don't think it's easy to get that 4-digit accuracy. So that's one application. Another application which is very important is what's happening if I have the generation of heat inside the material. And there are many applications which are associated to this particular problem. I will only give 2 examples. The first one is in nuclear safety application, for instance. You have heat which is generated in the solid phase when you have the respect in the framework of the nuclear accident. So you have a huge subsum in the solid phase. The temperature will rise, and eventually you will have boiling, fusion of the solid phase, and so forth. So you need to understand that. This is an example. And I've done some work on the flow of superfluid helium in large hadron colliders. And you know that in these colliders, you have magnets, and they are essentially made of some sort of porous material in some places. And if you have and the beam in the collider is not exactly, does not follow, there are always some reflection, things like that. So there is some heat which can be generated in the system. And if you are not able to predict the behavior of the system in that case, you may have accident. For instance, the LHC in Geneva had a very impressive accident. More than 1 kilometer magnets were lost because they jumped into a system the situation they are not predicted. The problem is that it is cooled using superfluid helium. And in superfluid helium, lose its superfluidity at 2.1 degree Kelvin. So if you increase a little bit, you start with normally the temperature is about 1.8, 1.9. But if you increase a little bit, then you have superfluid helium, so there is no cooling, and that's why it explodes. So this situation is not an academic situation. It does have some importance in many, many applications. And I have two types of heterogeneous sources. I have homogeneous sources, because, for instance, of radioactive decay, and I may have heterogeneous sources, heat generated through some combustion, for instance, or magnetic induction at the interface between the two phases. So this is the black stuff is what we have studied so far. And now we have an additional ingredient, which are those free systems. Well, it's so I have a couple. I can work out again all those equations. So for the bulk equation, well, the homogeneous thermal sources, they just appear as averages. So not a big deal. There is no problem. I have a phi, and I just average phi, and I have the source term in the macroscale equation. Simple. Well, this is not straightforward for the heterogeneous sources. The heterogeneous sources is generated at the interface. So, but I know the interface in the macroscale equations. The only thing I have is that I have some interfacial flux here. So I know that some flux is coming in my macroscale beta phase from this heterogeneous source. But which part? I have some average of omega, but I have to distribute that in the macroscale beta phase equation and in the macroscale sigma